Welcome back. Okay, so last week, what did we look at? We looked at t-tests, and we looked at comparing two different means of two different groups. And what that looked like was, for instance, there we go. We had a one sample t-test where if we took a sample mean and we compared it to a population mean, then we had a paired sample t-test, and that is where you compare the means of the same group more than once. So think of a pre-test and a post-test. And then we had an independent sample test, and that was looking at two independent groups. So you're looking at a control group and then an intervention group. So think of something where someone tried an experiment. This could be a professional development workshop for a community. It could be it could be a number of things: blood pressure, BMI. We could go on and on. There's all these other ones, but those are the three independent t-tests. So the question is, what happens when we compare means with more than two groups? So prior we just had a control, an intervention, or the same group. But now what if we're comparing a lot more? Well, it takes a different type of test, and that is a one-way analysis of variance, also known as an ANOVA. So an ANOVA compares the means of two or more independent groups in order to determine whether there is statistical evidence that is associated with population means that are significantly different. This is also known as a one-factor ANOVA, a one-way analysis of variance, or between subjects ANOVA. For our practice, we will just say a one-way analysis and variance, or ANOVA. Let's just stick with ANOVA, shall we? These should be parametric tests, meaning that they're normally distributed, and they are generally used when comparing the means of two or more groups. So we'll get into what that looks like. So this could look at the differences between, say, two intervention groups and like one control group. It can also just look for changes over time from a control group, and then they begin an intervention, and then again as well, or maybe a third time. But a one-way ANOVA and the independent samples test compare the means of those two groups. So if the grouping variable has only two groups, so going back to our interventions, just saying an intervention of a control group and a professional development workshop, and then you could still technically use a one-way ANOVA, just like you would an independent t-test, even though there's two groups. That's okay. In fact, if you run an independent samples t-test and a one-way ANOVA, you should basically get the same answers. But the ANOVA will always ensure for anything after or more than two groups. All right, we have to make certain conditions and assumptions for our data set in order to run an ANOVA. First, we got to make sure that the dependent variable is continuous, and we have to make sure that our independent variable is categorical, just like any of the t-tests. We also have to make sure that the cases that have values are on both the dependent and the independent variables. You have to make sure that there's an independence of observations. So in other words, that there's no relationship between the subjects in each sample. And that means that subjects in the first group cannot be in the second group, so on and so forth. And no subject in either group can influence the subject of the other group. And of course, it should be randomized. Your data must also make sure that it's normally distributed, and it must meet a homogeneity of variances, and we'll go under what that looks like. There should be no outliers. And researchers also use a couple of other things. Each group should have at least 6 subjects, and there should be a balanced design. So in other words, there should be the same amount on in one group versus the other one. And so moving forward, I want to remind that these types of conditions and assumptions should be met in all of our practices. So when you take the exam, you should go over this checklist, which I should have put like a little note there that says note, but maybe I'll just put that afterwards. How about that? Okay, so meet those assumptions. Now let's do a hypothesis test for this. So we will do this in class, but I think it's just good practice for me to have that on hand for you. This is, again, what we need to do for all of our exam questions. We need to state the problem, the null and alternative hypothesis, calculate the test statistic, the p-value, and interpret that p-value based on the significance level, and we have to have a conclusion. So let's begin. Let's state the problem. We're going to open up pets.sav, and I'll do it here in a second. Pets as moderators of a stress response. This chapter follows the analysis of data from a study in which heart rates, BPM, of participants were monitored after being exposed to a psychological stressor. That sounds like a horrible study in the first place. Like, let's just really stress you out and see how your blood pressure goes. Like, I bet the IRB was very interesting. Participants were randomized to one of three groups. Group 1 was monitored with a presence of a pet dog. First off, we need to know what kind of pet dog that is, because I think that should matter. If you're in a room with like a Doberman Pinscher or a Rottweiler, do you feel as comfortable, say, if it's a Shih Tzu? Group 2 was monitored in the presence of a human friend. Okay, good to know. And then group 3 was monitored with neither a dog nor a human. All right, so again, imagine 3 different rooms. And in room number 1, there would be someone with a pet dog inside the room. And then in group number 2, there was just someone with a friend. And then group number 3, there was no one. They were just by themselves. Okay, so I think I know which one I would choose out of these. But I really wonder how they stress them. That's the part I'm really wondering. But that's beyond the point. However, you should always consider these types of questions. Okay, so what does this look like? It looks like the null hypothesis would be that all the population means are equal. All right, so up at this top here, we have our mean 1 of group 1. We have the mean of group 2 and mean of group 3. And we're basically saying, and the K is just like, it goes on forever however many groups that there are. Because again, ANOVAs are helpful when there's more than 2 groups. Okay, so basically the null is saying that across all 3 rooms, all 3 groups, that they should be the same. So if I scared each one and their blood pressure remained the same, even the people with the dog in a room and then the people by themselves, and I tried to scare them all and their blood pressure got to the same level, then that is the null hypothesis. We would, eventually retain that. So therefore, the alternative is that at least one of the means, of the population means, is not equal to the others. So here is the example of the qualitative written form for this. So for the null hypothesis, there's no significant difference in heart rate when people are in the presence of a pet dog, a human friend, or neither a dog or human on their heart rate. The alternative to that is there is a significant difference in heart rate among individuals in the presence of a pet dog, in the presence of a human friend, and those who were not in the presence of either a dog nor a friend. Sad. All right, what does this look like? We're going to open up pets.sav, and I believe I should already have it ready to go. Let's find it. Okay. I'm going to make sure that this is where I want it. Sorry for the cosmic shuffle I just did there. All right. So, first off, what we always want to do, and again, this is good for the exam to practice. is that you look at this information and you say, let's find out what the descriptives are. So I'm going to go to Analyze. I'm going to go to Descriptive Statistics, and as I've mentioned in the past, I like doing Explore. I think that is the best, most robust way, and you will see here why. So I'm going to go to Explore, and I'm going to put the beats per minute in the dependent list in the group in the factor list. So factor would be considered the independent variable here. So this is where there's 3 different groups, right? We have 1, 2, and 3, and here's their heart rates. So this is what's at the top here on the dependent list, and this is our group. All right, so I'm going to go to Statistics. I'm going to, let's just check outliers, because remember, there shouldn't be any outliers, right? And hit Continue. Let's go to Plots. We are going to, heck, let's just add in a histogram, might as well, right? Let's do a normality plots with test, and we are going to spread versus level with the Levine test. We're just going to leave it at none. However, we are doing a Levine's test, and you will see that here momentarily. So I hit Continue, and then let's just see what it's in options. Let's leave that alone. All right, we hit OK. All right, so I'm going to pull up the other screen, and let's see what they show. I'm going to see if I can go back and forth with this. All right, so they did Explore, they did Plots, and they did, oh, look at this Levine test. Oops, I missed that. I could have sworn that I didn't. All right, so we will do untransformed Levine test. Let's go back to this. I'm going to exit out of this output because that's not what we wanted. I tried to guess. I completely forgot about that part. I looked at it and thought, let's just continue. All right, so I'm going to go to Descriptives, Explore. And real quick, I'm going to fix that. That way I don't mess that up again. All right. So I'm going to go to Plots, Untransformed. Hit Continue. That's the only thing that we need to change. And I can just show you right here now. We have the beats per minute, we have the group, we have factor, stem and leaf. I added a histogram. That's okay. Where's my plots? Where's my plots at? All right, and then I always do the normality of plots test. Don't worry, we might not even talk about it based on whatever this PowerPoint presentation is. And then we're going to do untransformed. Okay, so hit Continue, hit OK, and let's start off with this. What did we get here? Go to this, go to this. Well, my curious bystanders, we have, first off, these are the stem plots, all right? And we can tell that there definitely is some differences. Okay, we notice that the range, we do go from, you know, the 50s to the 100s here, and with their friend present, they definitely got the most rattled. If we're looking at blood pressure here, people with the pets, they look the least rattled, and then we have with just them being by themselves. Interesting. It's just almost a little bit more. At the peak, it seems a little bit more in the centered and more evenly distributed than the friend present. Okay, so let's look at the box and whiskers. So we have, we do have an outlier with the pet group. So it looks like someone still got startled. We don't know what kind of dog, again, what's going on here. Yep, we definitely see that the friend median is the highest among the control, friend, and pet. And then we have a little reminder that you can use the histograms. All right, and so we are now looking at Levine's test. So think of Levine as kind of like this, kind of like a bouncer to like a club or something. Like Levine, you got to pass Levine's test, and you know it's always like, oh, Levine. You know, sometimes you can still get by, you know, with not passing Levine's test. But, you know, for our purposes, let's see how do we pass Levine's test? So within this, we are looking at, first off, we know that within our null hypothesis that all standard deviations should equal the same. And versus that at least one of the standard deviations differ. Okay, so within the output, we look at this with an f-stat and our df of 2, and we look at our p-value of 0.943. Okay, so here's, that's a lot to say, and I want to kind of just bring it in. So what a Levene's test is that it looks for the equivariance, also called homostasticity. I always mess it up. I'm sorry, but it's there. But basically, we're looking for an unequal variance. That's what Levene's test is looking. It's saying, hey, how equal are all your people that are about to come by? You know, you have 3 different groups. How do they look across the board here? Okay, this is done through certain stats that are found in the book. Here's the beautiful part. Based on what we are doing in class, we don't need to memorize and fully go into great detail for this purpose right now of what this is. What we are primarily looking at is the significance and whether it is significant or not. So again, there's a p-value to this, and that's what this test of homogeneity of variance is looking at. So for the next slide, what do you do when Levene's test is significant? So again, right now, when we look at our results, which is 0.943, and I'm going to open up, let's just make sure that that's what I got. So I'm going to scroll down. So again, here's where I can look at the mean, the median, the variance, standard deviation, you know, all the fun descriptives. Like this is what you would copy and paste in for the exam. Putting that there. All right. So we look down at test of homogeneity of variances, and look, we got 0.943, meaning, again, if we're looking at a significant threshold, and usually we look at an alpha of 0.05, this is very far from it. So within a Levene's test, think of it as almost some like opposite of you know, when we're trying to find statistical significance. When we want to find statistical significance, we are wanting a really small p-value that is less than 0.05. However, with this Levene test, Levene is actually looking at the opposite. Levene wants to make sure that y'all are at least have some sort of commonality. Because again, when we go with a smaller p-value, that means that there is a bigger difference. So with the Levene's test, we look and we see that this is not significant at all, meaning that we kind of passed Levene's test. We were able to kind of move on with the ANOVA. We're able to go into the ANOVA club, if you will. That was horrible. I won't say that again. Maybe I will. Maybe 2 more times. Okay, so what happens when Levene's test is significant? So what happens when you don't get a 0.943, but you get a 0.04? Uh-oh, it's significant. What's going to happen? Well, there's a few things here. And I'm going to try to simplify it in a way that's nice and digestible because we can talk more in class. So what do you do when it is significant? Well, you need to stay with just the descriptive. So just talk about your statistics and exploratory data analysis. If there were outliers, here's where you would remove it. So remember, actually, in this example, we did have one that was, we did have one outlier, it looked like. You also need to mathematically transform into I always mess up the word. I'm sorry. I'm just going to skip over it right now. But you got to make sure that basically the skew of them aren't going to be too much, and there are basically formulas to do that. We're not going to deal with that, so don't worry about this part. And you can also use non-parametric methods, which we will talk about now. So here is our test of normality, and you get this by going to that explore function, going to plots, and clicking the test of normality. So I'm going to look, and just real quick, we're going to go back to the PowerPoint, but I want to look at our output results. We have, I'm not even going to, okay, I'll attempt it. All right, it's Kolmogorov and Smirnov. Sounds like a drink, let's be honest. And then we have the Shapiro-Wilk. That one seems more Shapiro-y. And these are testing for normality. Let's see what we need to do with this. So if I go to here. All right, so we saw the Shapiro-Wilk test, and this is exactly what we just looked at. The Shapiro-Wilk test is more appropriate, again, for a certain size. And we can see from this table that pets, friends, and neither were normally distributed. All right, so what it's looking at right here is at the significance. We are looking at all of these, and none of them are below 0.05. So if this, from this test of normality, if you look and you find a 0.04 within the Shapiro-Wilk, that means that piece is closer or is significantly deviated from the normal distribution. So let's look at neither, pets, and friends. Okay, so we have a 0.114, and then we have 0.319, and then we have a 0.862. Whoa! Okay, so what we're looking at here is that basically 1, if you were to get to 1, that would be like the perfectly normally distributed curve that we have. However, we can see that there is much more of a skewness with the pets and friends. So let's just go back to the box and whisker. We can see some of that here. Or I meant to say stem plot. So we can see some of that here. So remember, this is the 0.8 something. And it has, by looks, the most normally distributed factors. Now look at, within our pet present, we have an outlier, so that's also throwing some things off. And then with our friend present, we can definitely see a skew, as I mentioned earlier. So this allows us to even look at the data even more as investigators and say, well, is this data worth playing with moving forward? So you could almost say maybe this Shapiro is like Levine's backup. Like Levine said, yeah, y'all aren't significant enough, y'all can go on ahead. And then Shapiro's like, well, hold on now let's just see how symmetrical you really are. All right, so the first one looked at the different groups within it, and which is where we were able to look at this from the Levine's test. All right, so we based it on the mean. Then we looked at the test of normality. All right, so now we look at the descriptive groups, and this is just good to look at and to confirm your confirm your median or mean and standard deviation with any other additional information that you have about your data, especially when you collect it yourself. So we are looking at 3 different t-tests, okay? So again, the prior week we were looking at, just 2 different t-tests. It's the control and the intervention, the pre and the post, the sample and the population. Whereas now we're looking at sample 1 to sample 2 and sample 3, and sample 2 to sample 1 and 3, and when sample 3 to sample 1 and 2. Okay, so there's 3 of them, right? So it's just consider as each one is looking at the other one, all right? It's a triangular standoff, and we need to perform separate t-tests basically, and that's what an ANOVA is. You're doing t-tests for each one of those, but you're still combining everything, knowing and representing all groups at the same time. So within that comes the family-wise error, and this is the probability of at least one false rejection of the null hypothesis. All right. So what this table is showing you, and it is in your book, is that the more groups that you have, the more likely some of your information is not going to be accurate, because there are basically formulas that go on behind that. But just again, for this purpose in ANOVA, just know that if you were to have a group of 3 different groups, okay, 3 different independent variables, and then you also do an ANOVA of a group with 9 independent variables, Well, those 9 independent, like if you find statistically significant information in that group of 9, there's more of a chance that that's incorrect. That's what we're going at with this. So there's a 2-step approach to looking at the overall significance. We need to test the overall significance, and then we need to do a post hoc comparison on individual groups. So the first one is we're going to say, it's basically saying, is there any significance at all amongst these groups? And it's going to be like, it's either going to say, nah, don't worry about it, retain the null. Or it's going to say, yeah, actually, there is significance. Okay, well, where's the significance? I don't know. That's what the first one is saying. And when they say, I don't know, they're also saying, go ask post hoc. And post hoc will tell you which groups are statistically significant from one another. So let's find out within our world. So for an ANOVA test, a null hypothesis is that all groups are equal, and you use an F test for this. Same as a Z table, same as a T table. It's just a different formula to do this. Excuse me, I need water. All right, the F test is a ratio within other equations that basically focus on between and within groups. We'll get to that here in the next slide. All right, so then the p-value from that F test determines whether there is at least one pairwise difference. So, if we're looking at the p-value in this, and then we can better reject and conclude that there is significant difference between at least one of the pair means. But then the post hoc tests are used to test the pairwise differences in between. So again, this is something that you don't need to do by hand, and I just have it here, but you're basically looking at the equations between groups, and then you're looking at the differences within the groups. I think of it like those almost like I don't want to call them holiday dolls because they can be any time of the year, but one inside the other. They're basically used at different areas, and that is how we find the F statistics. So again, it is a ratio, and I wanted to keep this part where it says the signal to noise ratio. Think of noise as something that you kind of can't see, but it can cause disruptions. For example, if you were to, and this is actually like a literal example, but it gives you the idea, is that if you have your cell phone next to a bunch of electronic equipment and you're using Wi-Fi and Bluetooth, there's more signal going out and other things are affecting it. So then if you have speakers all around that cell phone, the chances of those speakers picking up incoming and outgoing information are going to be greater. That's what the F-stat is basically looking at in numbers. So we look at let's look at the mean square between the examples. So here is our n, we have our means for this. I'm not going to go into too much detail on this. Honestly, this is something that is in the book. If you're interested, you can move forward with it. But because I want to just get back to the ANOVAs for this. All right. So within the ANOVA, we get an F-stat of 14.08 based on the information that we have. Now, let's actually do this within our stats. Okay. So we have the descriptives, we have the extreme values. We can look at this extreme value. It looks nice, okay, but what's even kind of quicker within all of this is if you scroll down and you can actually see if there's like an extreme. And so, like for instance, there's one extreme here. There's no extreme in these two, so there's clearly an outlier. And what I really like about that Explore feature too is at the very end you got that box plot. How nice is that? All right, we're going to find the F-stat. We first go to Analyze, General Linear Model, Univariate. We are going to put the group into fixed factors and the beats per minute in that dependent variable. And then because I got in trouble last time, I jumped I jumped the ship too early. Let's go back and make sure that we're doing this right. All right, so we have the group, and then we're going to go to options, and then we're going to bring the display means for the group. So I'm going to come here, and I'm going to go to options, and oh, there's an F test right there. I just want to click everything because it's just so much fun. But hold up, first we want to do a post talk, and we're going to display it for the group. And I'm going to choose LSD and 2K. And just for the fun of it, I'm also going to use Bonferroni. I'm going to hit continue. All right, what else you got up for us, PowerPoint? All right, so we went to options. Oh, we needed to go to options for that. All right, so let's go to options. Looks a little different than how it used to be. So you know what? I'm just going to hit display homogeneity. And we'll do that F test. We should. All right, and then let's go back to this. What else you got for us? We added the group. We added these two. All right, good to go. All right, let's see what we get. We hit OK. Da 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 da. All right, we have the between subjects. This just shows the N and the different labels. We have the descriptives. We have the mean, standard deviation, and the N. Hey, there's our good old friend Levine. Hey, remember us? No, we good. You already checked us. All right, we're good to go. All right, we have the F test. And again, this was not within the PowerPoint presentation, so I'm not expecting you to do this. I was just curious as to what shows up. And it shows the dependent variable. It also shows the significance. And then we can scroll down. And then we look for test between subjects. And what we have here, or right here, this group, what we have here is we have a group, and this is looking at between the groups. So again, we have 3 different groups, so it's looking at the differences between those. And then we have our error, and that is looking at within the group. So the actual groups inside of each of those 3 groups. All right. And that's where that is. So from this information, and this is what we just looked at, I did not hit partial eta squared. I apologize for that. We just left it at that. But we know that at least one of the population means differs. But again, this F test does not tell us which one. So what do we look at? We look at the post hoc. So, sorry. The reason why this partial eta squared is because this information right here, the effect size, is not in our book, but this gives you an idea of the strength of the relationship, so the effect sizes, and we know anything between, and we know based on this information that anything between 0.2 and 0.5 would be a small to medium. So let's look at that post hoc, shall we? This looks at the comparisons pursued after the rejection of the ANOVA. So we just rejected the ANOVA null hypothesis where we delineated the differences, but which of the groups differ out of this? So when performing large numbers of tests, the data increases the chance of a type 1 error as the number of tests increases. So remember, we already talked about, if you have more tests within it, you have that error chance you have that increase in error chance. So any adjustments need to be kept to resist or prevent a type 1 error, and that's where the post hoc can come in. And from that, let's see what we get. So again, within this, we look at the family-wise error rate, and we look at the probability of basically error that's going to happen. This is going to look at, and we already actually did this information. We already have this information in our SPSS. We have here the 2Ks and the LSD, and this is going to look at the actual significance between the individuals. So with an alpha of 0.05, our p-value ends up being very, very small. And we can conclude that the heart rates are an indicator of the effects of stress differed between the following groups. So here's the information. You can read it yourself, but I'm actually going to go back to what it looks like. So if I go down here, we are going to find 3 different of the post-hoc groups. Again, so these post-hoc groups, they're kind of like, think of them as, okay, so I'm sticking with this horrible analogy. You went to Levine, the bouncer, checked you out. They said, yeah, you're good to go. You're not significant enough. And then Shapiro Wilk was like, all right, so amongst you, are any of you, too wobbly, or can you all at least have some sort of evenness at normally distributed frequencies? And then, everyone's not significant again. Okay, all right, move along. So then you look at, as the ANOVA, based on the F test, as the ANOVA's groups, are there any significant differences between the 3 groups? Again, we have the one with a pet, the one with a friend, and one with neither. And so we did find out that, yes, there is significance, all right? And we see that here, right there. All right, and we found out that, yes, among the groups there is significant differences, but we don't know which one. So then we go to the post-hoc. And that they're now deep back into the club, and they're looking at you. But they all look at you in a different way. So 2K, LSD, and Bonferroni, they all look at you differently. Let's look at the numbers to see how. So look at the significance spot, or this is our p-value. And it separates each of the independent variable and compares them to the other independent variables. So we are looking at the differences between pets and the room with a pet and a room with a friend. And there is a significant difference in the heart rate from the group with a pet in the room and the group with a friend in the room, all right? So, and again, we saw that even on the chart, but now we have proof, based on our test here, our post-hoc test. All right, so then when you compare the pets with the group with no one in the room, there is our p-value is larger. Yes, it is 0.027. So it's definitely showing up, but that is still under our alpha level of 0.05, meaning that there is statistically significant differences for the group with a pet in the room and the group with nothing in the room. All right, moving over to friends. Let's look at the friends. So the group with a friend in the room. So we already know that the group with the pets is statistically significant. In fact, this number right here, this third row down, is the exact same as the first row down. These are looking at the same thing. It's just switching on who you're looking at as their first group. All right, now looking at the group with a friend in the room as compared to the group with no one in the room, the p-value is 0.032. Okay, that's even higher. However, there was higher than the pets and the neither, but that is still statistically significant. All right, well, just based on this, that across the board, all 3 groups have significant differences among the groups, and in fact, all 3 groups are statistically significant from one another based on this information. Now, again, there's 3 different people, there's 3 different groups looking at you, the 2K, the LSD, and the Bonferroni. So within these, if I look at the exact same thing, because again, these are the exact same results, and it does it in order from pets, friends, neither, pets, friends, neither, pets, friends, neither. All right, so let's just look at where's that our p-value was with pets and neither. So if I look down here, or I'm sorry, with friends and neither. So we have friends, neither. And it is our p-value is 0.012. All right, now let's look at Bonferroni. Let's get that out of the way. All right, pets, neither, 0.037. All right, what I'm showing you here is the p-value of the exact same thing from the outlook of 3 different tests, 2K, LSD, and Bonferroni. And from what this is gathering, you can see that the 2K is in the middle of this p-value, all right? So it is at 0.032. I'm just to the side, I'm going to write that, 0.032, all right? The LSD is 0.12. Whoa, I didn't mean to. I thought that was, I thought it was Excel. All right, so this one is much smaller, all right, much more significant. And then we have the Bonferroni, which is 0.37. So this one has the highest p-value, whereas the LSD has the lowest p-value, and 2K has the middle ground. So you could, in some stances, you could say that the Bonferroni has the most conservative approach, or it looks like it has the most conservative approach on something that is statistically significant, whereas 2K is kind of in the middle, and then LSD was definitely much more significant than 0.037. So just showing you that there's 3 different ways. All right. So the data are arranged to the form an ANOVA table, and that is the test between the subject effects. And again, I'll just show you what this table looks like here. In fact, I hope we did it on this one. It has different models right here. It is there. But we need to do an ANOVA test to actually get to that exact table. All right, and there it is. This shows that there is significance amongst the groups. And that being said, this is how you would actually explain it full out if you were doing a manuscript. All right, there are sample sizes, and this affects how the ANOVA would work. And I'll just say right now, this is kind of beyond what we need to really focus on, but it is incredibly important if you want to continue publishing and doing deep statistical analysis. All right, what happens when it is a non-parametric test? Well, we use the Kruskal-Wallis test. And that is when the normality isn't met, when homogeneity of variances aren't met, or there's outliers within a one-way ANOVA. Going back to the example, Levine said, you know what, you're actually kind of significant. I don't know. And then you got Shapiro-Wilk, and he was like, whoa, yeah, y'all are significant. Even if one of them says that you're significant, then you would have to do the Kruskal-Wallis, or if you have an outlier in there. So this is based on based on ranked transformed data. So we'll see what that looks like. And basically, we're looking at it more as an ordinal, and we get to a chi-square, which is actually something that we will be covering next. Look at that. All right, so a KW hypothesis test. We are looking at the median, and it just depends on how many numbers of groups there are. But we are going to do this in class just to practice again, but let's just do it now because I want to practice as well. Yeah, I've done it plenty of times, and then you do it again, and then you forget something, and you get scared, and then you have hiccups for 3 days. Okay, so it asked me to open up survey, and I noticed that survey is not here. What happens when you have a non-parametric test and you have an ANOVA that you want to run an ANOVA, but it ends up being that you have a non-parametric data set? In other words, there's some skewness, there's some outliers, or there's some too much variance between the groups. So going back to the horrible analogy, you walk up to the club and Levine looks you up up and down, left and right, and says, you know what, actually you are significant. Your p-value is below 0.05. And then, or you go to Shapiro-Wilk and it's like, oh, you know what? Yeah, y'all, there's significant differences between you. If that happens, then you actually don't get into the club. You got to go to the club right next door, and that is the K-Dub, or the Kruskal-Wallis. And we will be practicing this in class, but just know that this is a non-parametric test in lieu of an ANOVA. And we'll be using the survey. I'll be providing that data set. And this will just walk us through what we need to do, and it will provide where our significance lies amongst the groups and what that looks like. And then we would continue interpreting the data. So we can continue on, and within next, we would look at comparing two or more groups over time. This is also a one-way ANOVA, except this is that the average differences between paired matched samples. So think of a weight program before and after a dietary program. You also have, like, say, a control group within that. So then you have three different ways. Or three different means to have. So within this, it needs to be exposed. The subjects need to be exposed more than 2 different times. So the example that I've given in class is I've done research on professional development workshops where educators come to class or come to a workshop, and we survey them before the workshop, we survey them after the workshop, and then we survey them 6 weeks from there. So that would be a one-way repeated. This data should be measured on the same scale, so everything should be the same. Survey should be the same. So if you were to ever do something like this, don't ever change it or manipulate any of the questions, add or subtract anything. Everything should be the exact same. And you need to make sure that you have independent variables that are categorical, and then you got to test that if there's significance between them. So again, these should be normally distributed, and any non-normal populations, especially those with like thick-tailed, should be considerably reduced based on the power of the test. And so you can lower the power, which would help, but you're also running into some efforts with sample sizes. That is where sphericity looks at the differences or the variances among the different groups and all the possible combinations. You'll use a Maltese test of sphericity, and just like as previously stated, hypothesis testing: state the problem, null and alternative, calculate the test statistic, p-value, interpret that p-value, what's your significance or alpha level, state that alpha, and then state a conclusion. So as here we have an example, and in fact, I'm not going to go too much into this just because this will be we will be using information we'll be using a data set for class for this, and this is just the how-to. I will provide those if you want to get ahead of the game. And then a Shapiro-Wilks test, we've gone over this, and we've looked at the difference, but you can still run one of those if you do, like, say, the explore function. And just by even looking at this real quick, let's just stop. I know you've made it this far, and if you haven't, I'm sorry you're missing out. But if we look at the test of normality, we go to that Shapiro-Wilk. I can see that there is almost a statistically significant difference in the confidence in that first time. So even without knowing this information, I'd be weary of anything coming out of the confidence time number 1. But we'll talk about that in class. And then we'll try another one here with a one-way repeated measures ANOVA. And this is where we are going to have 3 different levels at 3 different time points. We're gonna look at it. We're gonna look at it with a confidence interval adjustment of Bonferroni. So I know that this part can kind of be confusing, and where are we going? This is almost like the stuff where when you and if you continue doing statistics and data, these are the things that you're really going to have to truly consider. Find the literature that goes behind whatever study you're doing, because everything is going to look different based on what you are going to study, what your data sets look like. And this gives you a nice, very glossy example. And so it's something that we are covering here, but we won't go extensively in class. But just know that this exists. So looking at the data, making sure that everything's good. Within a MANOVA, you actually do you look at Wilks lambda, and again, these are all different types of looking at the same thing. For instance, I had a study where Roy's largest root had significance, but none of the other ones did. Again, so these could be, considered liberal or more conservative based on how they equate from the F-stat and the values. And, even just looking at this, there is clearly some significance. I don't even know what this information is. We'll find out in class. I know what it is, but what do we know in this video, right? Okay, so if we look at that eta squared, this is going back to our effect sizes, that we know that this is actually pretty darn strong, that there is a good strength of relationship within our findings here. And then when you interpret MANOVAs, you look at the significance, and right down the line we can see that there is significance between all of the groups that we have. So between the time 1 and time 2, there was significance. Between time 1 and time 3, there was significance. Between time 2 and time 3, there was also significance. And here are all of the different avenues. And again, some of these are the same. It's just showing you based on which first independent variable you're choosing. So it's shown, you arrange everything usually in a table that you want to provide, and you can write it out, and putting the Wilks lambda, for instance, as well as with the F-test that goes with it to show what it equals, the p-value that you were able to get out of it, and the eta squared is good to give a good number. So higher, the stronger the relationship between the multivariate rate. So again, if it's not parametric, if it did not pass, the Levine and the Shapiro-Wilk, if they were significant in that, then you got to go with the Friedman test for non-parametric. And we're gonna do this one in class as well. We're gonna have to do this one as well, because I'm on a different computer, so I'm unable to, unfortunately. So let's save that for class. Looking forward to it.